let me give you a very simple model, okay? So I'm going to combine two things that we know about the brain. One thing we know is that there's this idea of lateral inhibition in the cortex. Remember I told you about that. Furthermore, there is damped oscillatory return to rest. So this is an example of resonance. Does everybody here know what I mean by resonance? And if not, let me explain. Have you ever been on a swing? Okay? All right? So you know, if you ever watch a little kid on a swing, little kid will sit on a swing and just wiggle his legs like nuts, okay? Doesn't do any good, okay? Until he learns to do it the right rhythm, then you can get that swing to go. And I bet some of you guys did this. We certainly did when we were kids. You go all the way around. Try to go all the way around. It's really dangerous. They probably don't let you do that anymore. And some of you might have seen it. This is a great old video you probably saw in high school physics that I think it's called the Tacoma Narrows Bridge, okay, in Washington, okay, and this whole bridge goes berserk. Another great example more recently, and you think they'd have learned, is, and you can go do a YouTube on this one, YouTube the Millennium Bridge in England, okay? It's wonderful, okay? You have all these people, and they're walking, and it's exactly what happens is the bridge starts to sway a little bit, and if you walk on something that sways, anybody who's ever stepped in a boat knows this, you compensate by shifting your weight, okay, in the direction of the sway. So what that does is people that are walking like Popeye, but independently, that swaying starts to cause them to go together. And of course, when they go together, that induces the bridge to go more swaying. And pretty soon, everybody's doing this together, okay? And so that's an example of resonance. So what happens is there's a combination of lateral inhibition coupled with resonance. And so if you hit the visual system with the right frequency, then you can get amplification if the period comes every cycle like this, or every other cycle, or something like that. You get amplification, and that combined with this gives rise to an instability that gives that produces these dramatic spatial patterns that you see. Okay, so just like when you pump a swing, if you go at the right frequency, you can make the motion large, and this parametric resonance excites the cortical network, which then engages this lateral inhibition and produces these spontaneous patterns. Now I want to see if I have, I do have some sims of this. Okay, I don't actually have the sims here. I'm going to show you a video of it. Okay, here we go. Now, what you'll see is the pattern gradually emerges, okay? It'll get more and more high contrast. And this was also mapped through that complex logarithm so you can make it look more like a regular pattern. What I want you to see is that what's going on here is kind of interesting. The black and white are alternating on every other cycle, okay? And this is another really great example of the power of group theory and symmetry, understanding what's going on here. All right, now you can see the pattern is fully formed after only a few cycles. And again, I want you guys should try this and you'll see. Unfortunately, there's all kinds of crazy patterns in here. So the guy that made it, wanted to make lots and lots of patterns. So some of them work, some of them don't. Okay, so let me just take a brief aside. All right, it turns out that when you flash light on a cortical network, there are two ways that you can become unstable. Okay, so imagine that the whole network is going together like this. Okay. Now, if you look at at the stability. How do things become unstable in period? Do you guys know anything about stability theory of equilibrium? You know, you take a differential equation, you linearize around that, you get a matrix, and you look at the eigenvalues. Does anybody know it? I know Angela knows that. But,
I know at least 4 people in this.
some of you guys know that, okay? All right.
6.
Well, this is a little different. Here, there's periodic stuff going on. So instead of looking at, let's look at what the system is after each cycle, okay? So you get a matrix, okay? So after each cycle, you start with a matrix A, and then after the next cycle, it's the same matrix squared. A squared, A cubed, and so on, okay? So imagine I take a matrix and I take its nth power, okay? Then I can ask, what does the nth power of that matrix do to some vector, okay? Now, you guys probably know about eigenvalues and eigenvectors, right? So if you take a matrix and you apply it to an eigenvalue or eigenvector, you get back that with a scalar factor called the eigenvalue. So if you apply a to the n on a vector, you'll get the eigenvalue to the nth power. Now, you want to know whether something's stable. You want that nth power to go to 0 as n goes to infinity. So that would mean that let's imagine we only have real eigenvalues. The absolute value of that eigenvalue has to be less than 1, right? So if it's negative a half, it'll be a damped oscillation. So it turns out that in these cortical networks, that when you periodically force them, only 2 things can happen. You can have an eigenvalue that becomes greater than 1, or you can have an eigenvalue that becomes more negative than -1. Okay? So it turns out that if it becomes more positive than +1, that leads all the time to, that always leads to checkerboard type patterns, okay? And hexagon type patterns. Whereas if you go through a -1, because you get this additional symmetry, that always leads to stripes. So it turns out that using this symmetry idea, you don't need any model at all. It comes purely from hardware. I mean, just mathematical hardware. What's really cool is experiments have shown that at low frequencies, people see hexagons, and at high frequencies, they see these stripe-like patterns. And that's almost model-free. It's almost independent of model. All right. So basically, you see those form constants.